So now we're going to start looking at conservation of momentum. So we're going to do a lot of these problems. This is one of the biggest aspects of linear momentum you're going to deal with, is that momentum is conserved. Now, momentum is only conserved as long as there's no outside forces on it. Because one of the things that we talked about is, with the impulse momentum theorem, is in order to change the momentum of an object, we need an outside impulse or an outside force. Okay? No impulse means no change in momentum. So that's the scenario we're talking about for conservation of momentum, is that there's no outside force in the system. So train cars are coupled together by being bumped into one another. Suppose two loaded train cars are moving towards one another, first having a mass of 150,000 kilogram and a velocity of 0.3 meters per second. And the second having a mass of 110,000 kilograms and a velocity in this direction of 0.12 meters per second. The minus indicates direction, but what is their final velocity? So when they hit each other, if I think of the system as two of these cars together, when they hit each other, there's no outside forces. Yes, there's internal collision force, but there's no outside force on the two objects. So in the collision, we would say the momentum before equals the momentum after. So the momentum before is the sum of just the mass and velocities. So this one is 150,000 times 0.3 plus 110,000 times negative 0.12, and that would be 31,800 kilograms meters per second. Okay. What is their final velocity? So they're coupled together, so when they hit each other, they move together as a single unit. So the single unit must have the same momentum, the mass being 260,000 kilograms times whatever velocity that they're at. So velocity would equal 31,800 divided by the total mass, 260,000. Because once they're moving together at the same velocity. .122 meters per second. Consider the following question. A car moving at 10 meters per second crashes into a tree and stops in 0.26 seconds. Calculate the force the seatbelt exerts on a passenger of the car to bring him to a halt. The mass of the passenger is 70 kilograms. So F delta T, M delta V. So the F is equal to M delta V over delta T. Okay, so if I were to calculate this, we're only considering this question. I don't know if we're supposed to solve this one, but 70 kilograms. His change in velocity as he goes from 10 meters per second to 0. So his change in velocity was 10 meters per second in 0.26 seconds. And let's just see what we would get, just as a practice. This is 2.6, and this is 2690 newtons. Okay. Now, would the answer to this question be different if the car with the 70 kilogram passenger had collided with a car that is mass equal to and traveling in the opposite direction at the same speed? No, because if I had two objects same speed going in the same direction towards each other, the total momentum is 0, right? If I were to add up the mass times velocity and the mass times velocity, because they're moving in the opposite direction, the total momentum 0. And so when they collide, they're stuck together and their total momentum 0 again, because there's no outside forces on the system. And so the person would still come to rest. So he's had the same change in velocity, maybe the same time. I mean, the real question is whether the time would change. If the time would change, then yes, the force would change. But if it took the same amount of time to collide, then this calculation would be the same. A 1.8 kilogram falcon catches a 0.65 kilogram dove from behind in midair. What is their velocity after impact if the falcon's initial velocity is 28 meters per second and the dove's velocity 7 meters per second, same direction? So the momentum before is the 1.8 kilogram times 28 meters per second plus the 0.65 kilograms traveling in the same direction, so also 7 meters per second. We just make it plus, and we would get 50. We'll call it 54.95 kilograms meters per second. And then afterwards, they're moving together at the same speed. And just assume the moment right after, there's sort of like no force to cause a change in momentum. Momentum after is the same, and they would move together as a single mass times some velocity. So v would be 54.95 divided by 1.8 plus 0.65. .4 meters per second. Hopefully it makes sense that they would slow down, or at least the falcon would move slower because the dove was already moving a little bit slower. Thanks for watching. If you enjoyed this video, I go through a lot more of these exact kinds of problems with much longer videos on my website. It's entirely free. Check out the link in the description below.